Hello, good morning, everyone. This is the second class of today. Today is 8th April 2020, and today's second class is basically from first year chemistry. So, in first year chemistry in the classroom, there are 8 chapter total, I guess. We have done 6, only 2 are remaining, the 6th chapter and the 8th chapter. So from today we are starting the classes, and the 6th chapter, chemical equilibrium, is going to be, we're going to start it from today. I will teach you here, I teach you in the classroom, and you will fare your work, you used to do, and you can share your work back to me from your parents' number, or if you have a phone, then from your own number. Just take the pictures of your copy. All of you have copies. In our school, we always do this, and fare it the way I used to instruct you. And once you are done, take the pictures of those work and you can send me. I will comment back, appreciate, or maybe correct few mistakes if there will be. All right. This class is exclusively for first year students, but as you know, in our college, it's basically for all the improvers as well as the students of class 12. The improvers in class 12 students don't have to fare this because they have done already. They can just make some points for my lecture and write the points and share with me their progress. Otherwise, it's fine. They can just learn from it directly. If you will send me your homework, it will be better, because then I will understand your progress and also give you my feedback on your work. So let's begin with our new chapter. It's 6th chapter, chemical equilibrium. All right. Now, equilibrium, it means balance. And this topic basically is from physics. There's a physical equilibrium, children on a seesaw, right? A book something is placed on a table is in equilibrium because the forces are balanced, downward force, upward force are balanced. So this is physical equilibrium. And but question remains, what is equilibrium doing in chemistry? And what kind of equilibrium is in chemistry? So to understand better chemical equilibrium, I will first tell you the 2 major types of chemical reactions. So there are 2 types of chemical reactions on the basis of the extent until they go. Extent means how long the reaction can go, for how much time the reaction can go. So on the basis of extent, there are 2 types of reactions. One, the irreversible reactions, right? And the other type is basically reversible reactions. So reactions take place everywhere. They take place in the laboratories, they take place in the factories, and even the kitchen. Chemical reactions taking place because different substances are reacting to produce new things, and they are important for us and commercially and personally. So most of these reactions are irreversible, which means when the reactants react with each other, they form the product, and the product they don't react to make the reactants back. Let me first make you a general representation of a chemical reaction, which is called chemical equation. Now, A plus B, it forms C plus D. Now, let's say A plus B are the substances which are reacting with each other. They are called reactants, right? And C and D are, just suppose, for example, are the substances which are basically being produced. So they are called products. Now, reactants, products. Now, you can see this arrow has only one direction. which means that these AB can become CD, but CD cannot become AB. This is irreversible reaction. This is how we represent the one-way reaction, irreversible reaction. Let me show you how we represent the reversible reaction, and that will be a kind of surprise for you. Let's say A plus B are two reactants, suppose, and C plus D are the product. So what difference do you observe in these two equations? Can you tell me, or can you think about it right now? Yeah, the difference is in the arrows. This is arrow showing they can become this. This is a special type of arrow in which there's a directing from left to right and from right to left. This tells the possibility that the reactants can react and form products, and the chances of the products reacting and forming the reactants is equally the same. Now tell me which of these reactions are going for completion. Okay, will this complete ever? No, because AB will make CD and the CD will also react to make AB, and this will go on and on and on and on. Reactants converting to products, at the same time products converting to reactants. Concentrations are not changing, but the reaction is taking place within inside. These are the reversible reactions, and these reactions are called the irreversible reactions, in which the reactants will react and form a product sooner or later, but the products will never come back to the reactant. These are called one-way reactions. They always go for completion. So these reactions are called one-way reactions. They go only in one direction, and they are called both-way reactions. It means that they go either way. Such reactions always go to completion, which means they are going to complete. Some reaction will complete sooner than others, and some will complete later than others, but this will definitely come to a stage where no reaction will continue, and this is a reaction which never go to completion, because the both-way reaction will allow the reactants to react to make products, and at the same time products will react to make reactants. This process will continue for infinitely long time, and there is no completion for the irreversible reaction. However, there is always a completion for the reversible reactions. Next thing is that the reactants completely react. Reactants consume, completely. Now here I want to make a clarification. Both reactants or one reactant, when it completes, reactants go to the end. In this case, reactants are always present in the reaction vessels or beakers, just as the products. Now it depends on how we control the reaction. We can shift it anyway, but both reactants and products are present in reaction vessels or beakers or whatever is the equipment used. So this reaction is time dependent. It is going to get done with time, sooner or later. Okay, these are independent of time lapse, because they continue forever. Okay, they come to an end and they never stop. So these are two basic types of reactions in chemistry based on extent of reaction. Now, extent, the word extent it means limit. By limit, it means how long a reaction can go. Right? So they have some extent. They can have less or more extent, but they have infinite extent. They just go on and on and on. Now, just let me explain to you in an easier way. You make food in the kitchen, you cook the chicken and make whatever you call it, dish for you. There is no way that the dish will become back to the chicken. Once it's gone, it's gone. You put milk to make tea. Can you get the milk back from the tea? No, right? So most reactions are irreversible in this world, whether they are in the industry or laboratory or kitchen or wherever. This is interesting because it's rare, and I thank God it's rare, because because the reactants can make products and the products can make reactants. In this way, this could be dangerous. For example, if making of cement was reversible, it is not, okay? Don't worry. If it was reversible, then you make cement from gypsum, calcium carbonate, and you make buildings from it. What if it converts back to the product, to the reactants, and the buildings collapse, right? So no way. We don't want these reactions. We want these. We like these reactions. So these are better reactions. They take place a lot. 90% of reactions in chemistry are irreversible. Some are reversible. For example, very common ionic reactions. If you take silver nitrate, all right, and you mix it with sodium chloride, all right, the reaction will take place, and Na will go to NO3, will form sodium nitrate and AgCl. Now these are the reactants and the products. Sodium nitrate and AgCl are two stable compounds within themselves. They don't want to react and come back to the reactant. This is an irreversible reaction. Many reactions are irreversible reactions, and that's good for them. Some reactions are reversible, and they are less in number. Now, can you guess this chapter, chemical equilibrium, what is it about? Is it for these reactions or these reactions? These are majority reactions, and you can be thinking that this chapter number 6 is about them, but unfortunately this is about them, because these reactions do not have any problem. We just mix the reactant and we know that the product will always form sooner or later. These reactions need our attention here, my dear friends, because we have to control them. We have to find ways of how to make sure that the reaction goes either just right if you need the products, or just left, depending upon what you need. And the 6th chapter, chemical equilibrium, as you can guess, equilibrium can be here. There is no equilibrium in irreversible reaction. Equilibrium only happens in the reversible reaction. So studying chemical equilibrium basically will help us understand how reversible reactions take place, how we can control their directions, how we can make more products, because a chemist combines the reactants to make products. Who will combine the reactants to make reactants? Okay, there's no point. So chemical equilibrium, the 6th chapter, is all about these naughty boys, the reversible reactions. It's about time that I give some examples of these reactions. For example, nitrogen reacts with hydrogen to form ammonia gas. Now, ammonia gas is used to make cosmetics, and it is reversible. Okay, this reaction was done by Haber, so it is called Haber's process. Now, Haber's process is a reversible reaction, which means ammonia can break down to give you these things. This is a reversible reaction, a very famous one. Next is sulphur dioxide. When you react with the oxygen, it makes sulphur trioxide. This is called contact process because sulfuric acid, which is the king of chemicals, used to make a lot of chemical substances, need sulfur trioxide. And the formation of sulfur trioxide is reversible, which means again we have to make sure we have more SO3, just like we have to make sure we have more NH3. NH3 is used to make nitric acid, sulfuric acid, both are important. Beside this, many others as well. You can see this is CH3, COOH, acetic acid. When react with C2H5OH, ethanol. This is the acetic acid. This is ethyl alcohol. Now, acetic acid is vinegar. Ethyl alcohol is obviously alcohol. When they react, what happens? This OH and this H form H2O. So you are left with a CH3, COO, and the H is gone. So this guy will take the place of H. It's going to be C2H5 and the H2O. This is water. This is called ethyl acetate. Now C2H5 is ethyl because ethyl is here as well. This is acetate, ethyl acetate. Now this is an organic compound and it belongs to a family of esters. This reaction is called esterification, which means formation of ester from alcohol and acetic acid. This is also a reversible reaction. There are many more, when you react hydrogen and iodine, they make hydrogen iodide, but hydrogen iodide can also break down back to the reactant. So this is also the example of a reversible reaction. You can also find more examples from your textbook as well. So this is the general introduction to the 6th chapter. It's about reversible and irreversible reactions. You can write down as a differentiate between the two, or you can write it down as just different topics. A question like what are reversible and irreversible reactions, or what are the types of reactions based on the extent of the reaction. If you have a textbook, you sure have. There you can open the 6th chapter and find the first page, and then you will find these instructions there as well. So the purpose of this video was to make sure that you get onto your books again and do your fair work, and of course share with me so I can tell you what are the mistakes and how can you make it correct. So I will take advantage of this opportunity and I will go to my next topic. The next topic is the chemical equilibrium. So this is the name of the chapter, chemical equilibrium, and the topic is also chemical equilibrium. And I will teach you what is chemical equilibrium in the details right now. It's our next topic. First topic is this, next is chemical equilibrium. So let us take an example of a reversible reaction. Just suppose we have M mole of A, it react with N mole of B, and it form X mole of C and Y mole of D. Reactants, products. Let us suppose it's a homogeneous reaction. By homogeneous reaction means all are liquid or all are gases, or reactants in the products, all of them are in the same phase. It's called, this is a hypothetical, which means imaginary, homogeneous reaction. It means that all the product and involved are in the same phase. Now, when the reaction starts, do you have CD when it begins? No, you have just AB. So you have a lot of concentration, a lot of quantity of A and B, and you have a zero quantity of C and D. Right? But as the reaction continues, the A and B react, and only forward reaction is taking place because C and D are zero. Okay? If I make a graph for you here, This is y-axis and this is x-axis, right? Hope it's clear. Let's say x-axis show time. Time is expressed mostly in seconds. Whatever units you can use, you want to use, you can use for it, all right? So time in seconds. Let's y-axis shows the concentration, and which means quantity. Mostly it's given in moles per dm cube. All right, so let us suppose we are here, right? This is 0 seconds, this is 5 seconds, this is 10 seconds, 15 seconds, 20 seconds, 25 seconds, 30 seconds, 35 seconds, and 40, 45, yeah, 50, 55, like that, okay? And this is 0 mole per dm cube. This is, let's say, 20 mole per dm cube, 40 mole per dm cube, 60 mole per dm cube, let us say 80 mole per dm cube, 100 mole per dm cube, and so on, so forth. Now, CD is 0 in the beginning, so they are here. The concentration of CD is here, right? And let's say AB is here, because AB is 20, 40, 60, 80, 100, 110, 110. Let's say AB were taken 110 mole per dm cube. Both A and B, 110 mole per dm cube, 110 mole per dm cube. So the graph will start for AB from the top to bottom, because as time extends, the concentrations decrease, right? So if this line is going down, what does it mean? It means the CD are getting less. Why they are getting less? Because they are converting into AB. So this goes up. AB is increasing with time. CD is decreasing with time. So what's going to happen? There will be a decrease in the quantity of the reactants AB as time passes, and there will be a gain in the quantity of CD as time passes. Initially, forward reaction will be the strong one because there's the only reaction. But as the CD are formed, depending upon how CD react with each other, they will start to react back. Yes? Only initially, CD will react slow because they are less in quantity. AB will react fast because they are more in quantity. But what do you guess? When enough quantity of CD are formed, what do you guess? There shall be a strong backward reaction, all right, to form the AB. Now, you might be thinking that all the AB will become CD, and when once AB is 0, now the CD will react and all the CD will become AB. That's not right. As soon as the CD form, they start to react immediately. And slowly, gradually, they convert into the AB. But since this is reacting faster, so they're getting less quickly and they're getting less like slowly. So there's an increase in their concentration and there's a decrease in their concentration. But the concentration never becomes 0. Like AB, like this AB is maximum and CD is 0. It's not like this that CD will become maximum and AB will be 0. No. As soon as a CD forms, maybe if CD are more reactive, they will be less in quantity than AB and still react as fast as AB are reacting. Or maybe they are more in quantity, but once their reaction speed will be balanced, the quantities will not change. Let me tell you this. Let me explain to you once again here. As the CD decreases, and then we see that the graph becomes parallel to x-axis. The graph becoming parallel to x-axis, what does it show? The quantity of AB was 110. At this time, it became 100, 80, 60, let's say 45. Now, at 15 second, 5, 10, 15, 20th second, and after 20 second, the concentration is 45, 45, 45, 45, 45. No change in the concentration of the reactant. Why? Because if they are reacting and getting less, why their amounts are not decreasing? Because the CD are also reacting and they are forming AB for you. Likewise, you can see the CD first increased, they continue to increase, but after 20th second, they are also constant. Let's say they are 110, this is like 100. Now they are constant at 100 and there is no change in the concentration of CD. This is the concentration of the products. This is the concentration of the reactant. Now kindly just look at this graph. The graph tells that the quantity of CD is not changing and the quantity of AB is not changing. Why? Because they are reacting to form this and they are reacting to form those. So the quantities lost from CD to AB are gained from AB to CD. Why is the concentration not changing? Because the rates, the speed at which AB is making CD and the rate at which CD is breaking down to AB, they are same. So when they are same, you don't see any change in concentration. This happens in all reversible reactions. Now, after this time, let's say 20th second, the equilibrium is achieved. So now can you guess and tell me what is chemical equilibrium? Chemical equilibrium is a state in which the rate of forward reaction, the speed of forward reaction, equals the rate of the reverse reaction. The quantities are not equal. See, this is 45, this is 100, okay? But the rates are equal. The speed at which these are reacting together are same. So what is chemical equilibrium by definition? It is a state, yes, of reversible reaction, which should be homogeneous, right? At which the rate of forward reaction equals the rate of reverse reaction. Once the both rates are equal, the concentration which was initially dropping now remains constant. Which was increasing now remain. So concentrations are not equal, but they are uniform. What? What is uniform and what is equal? It means if you are guessing that the concentration of AB will be equal to CD, that's not right. The rate will be equal to, the rate of the forward and backward will be equal to each other. Now I can make few more graphs to clarify this. Okay, I'll make a quick one. Now this is also equilibrium. Compare the two. In this case, the AB were more reactive than CD. That's why the AB gone really low, right? In this way, the AB and there is an equilibrium, but the quantities of CD are, it means CD is more reactive. As soon as a little bit of CD is formed, they started to react at the same rate, right? This is equilibrium. So these two are equilibrium. You must understand. At this time, equilibrium started, but because CD were very much reactive, so even with less quantities, their rates were equal to the ABs. And now after this broken line, the graph is parallel to x-axis. When the graph is going to parallel to x-axis, it means the concentrations are not changing. It means the equilibrium has been achieved. Now, chemical equilibrium is basically dynamic equilibrium. If you guys know, there are two equilibrium, right? Static, when everything comes to rest, and there's also dynamic when they are moving. Now, chemical equilibrium is dynamic because they haven't stopped. The molecules inside at the microscopic level still are reacting. Okay, reaction is going on. It appears to you as if the reaction has stopped. But since inside the molecules are still reacting at an equal rate, you don't see this change. Reaction goes on. So we can say that the chemical equilibrium is dynamic in nature. So my dear fellows, today I taught you the two topics. What are reversible and irreversible reaction, the 6th chapter introduction, some example and differences. What is chemical equilibrium and why this happens in reversible reactions only and why it's dynamic in its definition. I will highly recommend you to open your textbooks, and the way you do, it's a similar thing for you. Write your work and share it, and when you are done, you can just leave the pictures of your work done at this number. I will check with your name, of course, so I can identify, and I will check your homework and if there's any mistake, I'll ask you how to correct it. I hope the session of these online classes will be very helpful for you for class 11 now, and they will be regularly now. We will be posting the lectures at this time. It's 12 noon right now, but I don't know when I will upload this, but like up to 2 before 2 p.m. you will have these lectures available on this YouTube page, and you will do your work, and whenever you are done you can simply send it to me. You should also learn it, because we'll also have a test of this very soon. So stay safe, stay at your home and do your work. Let us invest our time. Let us not waste our time. Thank you so much. Goodbye.